this stuff gets a little confusing. So another just quick screencast maybe to show you the why this redox stuff is kind of important and sort of a big deal. So trying here to describe and explain the relationship between redox reactions, aerobic cell respiration, and the production of ATP. So we're going to approach this from sort of a cell energetics perspective. And we were talking at the beginning of the year about like energy flow and energy conversions. And we were looking at on the growth scale from, in terms of sunlight into organics, right? So now what we want to focus on is using these organics to then, so organics and energy stored here in the organic molecules and converting that to the energy stored in ATP. So again, we're going to be doing this energy conversion thing is a big deal. And we talked about the primary production earlier in the year, converting sunlight energy into the form of organic stored energy. So in respiration, we're talking about the organic molecules here, right? Organics over here. Right? These things are potential energy, right? And the result of primary production, right? Result of primary production. Pardon me. So the bonds of these organic molecules, there's potential energy stored in the bonds, right? Stored in bonds of, say one glucose molecule. But the cell isn't using the energy stored in the glucose molecule directly. The cell is using energy stored in ATP molecules directly to run cellular processes. So we need to do another energy conversion from the stored energy in glucose to the stored energy in ATP. Right? So we need to convert that stored energy here into stored energy here, here, and here. The process by which cells do that is a respiration process. The way that they do that is via redox reactions. So I didn't hit that energy conversion part before, but I wanted to sort of try and do that a little bit more here. So this is adenosine triphosphate, ATP. The stored energy is in the bonds right here of these three phosphate groups. These are all negatively charged, right, phosphate groups, and it's putting stress, it's putting on these bonds here. So these are high energy bonds between the phosphate groups. So when we hydrolyze ATP, hydrolyze, right, the hydrolysis of ATP, we're going to be breaking this bond right here. Right? This one breaks, and we release then energy. So again, this is this is the energy that cells are using. Cells using directly, right, this energy. Right? So we got to make this ATP molecule, however. So if we're going to make ATP from an inorganic phosphate and ADP, we need an energy source, right? Right, to do this, right, to drive this reaction in this direction, which is positive delta G. So look at the titles. The condensation of ATP is endergonic, right, positive delta G, and is coupled with exergonic reactions of respiration. Read the redox reactions. The redox reactions are going to be net negative delta G. So those redox reactions are going to be, the source is redoxes of cell respiration. So we need to do aerobic respiration in order to get this energy source to then make this bond right here, right, and to provide that for the cell. So again, converting energy here. We had seen this before where this is going to be what? Well, this organics are going to be oxidized to CO2, and in the process we're going to reduce oxygen to water, reduced to water. Right? This reduction right here is not really the big deal. This is kind of the big deal right here, where I'm going to be doing this, right? Taking the hydrogens away. Well, glucose here has many, many hydrogens on it. Right? In fact, it's got 12 hydrogens on it. And so we're going to be taking all 12 of those hydrogens off. Well, look, if what we're doing here, here's a hydrogen, right? And here's the carbon. Right? We're going to be breaking this bond right here and breaking this bond right here and breaking all the other bonds that have hydrogen attached to them. Right? So, well, this is really OH, but you get the point here is that we're breaking bonds. And so by breaking bonds, this is going to be negative delta G. Right? Breaking bonds, oxidizing, losing electrons, right? Oxidizing, losing. This is all negative delta G. Right? So by converting the energy stored in these organic molecules, right, into these ATP molecules, this is an energy conversion. This is respiration. Right? So these oxidation reactions are happening to generate this energy to drive this reaction here, right, which is positive delta G. Right? So this is going to be coupled to this, or actually the other way around. We're going to couple this reaction to this oxidation of the glucose molecule and other organics. Right? We just teach it with these organic, with the carbohydrates there. The reduction has to happen with this oxidation here. So even though we're going to be making bonds over here, the bonds that we're making, and this is difficult, I get it, the bonds that we're making over here are different. They're at a lower free energy than the bonds that we were breaking. Right? So the made bonds here between the hydrogen and the oxygen to get water, right, are at a lower free energy than the ones we broke, broken. Right? So even though these are positive delta G reactions here, right, these negative delta Gs are more than those positive delta Gs are, right, which is how come this can happen. Right? You can't just have positive delta G reactions without a negative delta G reaction happening that's greater than or at least equal to those positive delta Gs that you want to do. Right? So again, this diagram, again, these are going to be oxidations up here. These are going to be negative delta Gs. Right? This reduction down here is a positive delta G. Right? So this is reduction down here. And this generation of ATP, right, is a positive delta G. These details of what's going on in the electron transport chain we'll discuss a little bit, but suffice it to say that we have these electrons that are going to be going down a free energy gradient, and this is this negative delta G. But we wouldn't have these electrons moving down a gradient. We would not have these electrons moving down a gradient if we did not oxidize something here. So again, we're converting the energy stored in these NADH molecules to this electron moving energy, right? And then we're going to use these oxidation and this moving to then drive this ATP production. And this is also positive delta G down here that's making this water, but this is kind of the byproduct, right? So we're able to then do this right up here, this energy conversion, okay? Maybe, okay, I don't know. If you have questions or you're confused, please bring them to class. But again, I wanted to just emphasize that we're converting the energy along the way there.